Good afternoon, good morning or good evening, depending where you are. We have been attending and organising these 3D workshops for the past 20 years or so, and I'm really pleased that we've managed to pull together this online version this year. So thanks for everybody who has worked behind the scenes. I hope you've enjoyed the talk so far, getting a good overview of the history and the mechanics of 3D geological modelling from Keith and Kelsey. It's strange talking to a screen in my home in Nottinghamshire and not to a room full of people. But looking at the number of people listening in, we're certainly reaching a big audience, bigger than ever before. My name is Holger Kessler. I'm a geographer and geologist at the British Geological Survey and have been involved in creating geological maps and models for 20 years or so. In the past 2 years, however, I've been on secondment to the UK Geospatial Commission, an expert body inside the UK Cabinet Office, tasked with unlocking value from geospatial or location data. My focus has therefore shifted from the production of geological data and geospatial data to how we can make that data more accessible in order to make impacts, create value, and most importantly, help to tackle the grand challenges ahead of us as a result of climate and environmental change. The key messages I want to bring across to you in this talk are that geology is not of any value just in isolation. It needs to be integrated. It needs to be a means to an end and not an end in itself. Geology, or the geosciences, are a small but really important ingredient to solve the complex problems of the next decades. We need to integrate and collaborate with other agencies, universities and industry from all sectors: land use, agriculture, transport, economics, utilities, etc. So in order to achieve or unlock the value from geology and geoscience, we need to be viewing ourselves and our science as part of a much wider ecosystem or data infrastructure. I'll give some historic context, some case studies, and some examples of government policies and initiatives, and finish with some conclusions. The original role of geological surveys, as for example set out in the Geological Survey Act that gave birth to the British Geological Survey, was very clear. It was the completion of a geological baseline survey of a country, so building on the William Smith map here on the left. Detailed description of the purpose and the economic advantages of the Geological Survey can be found in a report by Buckland, Sedgwick and Lyle to the Board of Ordnance Survey, who was then the parent organisation of the BGS. These topics are of course very familiar to geologists and have not really changed as the fundamental requirements for geological surveys in almost 200 years. They are the finding resources such as coal and metals, information underpinning construction of roads, canals, infrastructure projects, access to drinking water, sustainable drainage, construction, and of course the relevance of geology for food production. Things have changed dramatically in the last 150 years. I'm using this diagram from UK Research and Innovation to illustrate how the British Geological Survey is today part of a large network of research organisations and departments. I'm sure the same is true for most other countries in the world. All these organisations have emerged over the years to tackle discipline-specific problems. All are producing excellent science, technology, data and models, but lots of it remains locked up in individual data silos. However, we do know that the Earth system does not function in individual silos or departments. Natural processes, as shown here, as well as human behaviour, are intrinsically linked and part of one interdependent system, the Earth Science System. Here just one diagram from the IPCC to express this. When doing the research for this talk, I stumbled across this wonderful quote by Dr. Moore from the University of Nebraska, and in his lecture notes he describes the merging of disciplines and sciences and the need for people to connect and look beyond disciplinary territorialism and integrate their science and moving to a post, if not even transdisciplinary world, and I believe that is very much needed to tackle the grand challenges I mentioned before. What does that mean for geological surveys? Well, this slide from the Geological Survey of Canada beautifully illustrates the changing focus, methods and technologies that drive the need for geological surveys through past and future industrial revolutions. Lots to take in here, but I'll just draw your eyes to the changing requirements and the changing technologies. So we've, in the past 2 decades, moved through creating maps, 3D geological models, and it's clear that the future is increasingly about making predictions about the future state of the Earth system. And here we see the first mention of the term, the digital twin of the Earth. So what is a digital twin? Lots of you would have heard about this term and some might be very bored of it. It is a digital replica of a living or non-living physical entity. It's used extensively in engineering, prototyping. One of the best examples perhaps to explain is Formula One. To monitor the cars, performance, the cars are equipped with sensors, information about lap times of the competition, the weather situation, the tarmac temperature is all being fed into a model. Also hindcasting from previous races and forecasting to decide when is the right decision to have a pit stop or change the tires. And what has this got to do with geology? Well, if you think of the Earth as a racing car, you can see there we're talking about a digital twin of a planet. It's the same concept. We need to make decisions about the future of our planet. We might have to engineer with a planet, and we need to make sure that our interventions have the desired effects and outcomes and monitor the Earth in real time, just like a racing car. Digital twins are being created for individual buildings and construction sites. They're being conceived for cities and even entire nations. So the Centre for Digital Build Britain, based at the University of Cambridge, is conceiving an interconnected set of digital twins to make up the national digital twin. This is where geological survey organisations and geologists need to be there at the table and get ready to plug their data, models and information in. The reason being that important questions and important interventions in the future, such as flood risk management schemes, disposal of nuclear waste, infrastructure programs, constructions of wind farms, changing to farming practices, all the interventions we need to do, carbon sequestration in the soil, deeper subsurface, all these require data information from geologists, but crucially in the context and integrated with many other data sources and disciplines, as this diagram here describes. I'm now going to give a very brief demonstration of what I believe is a really good visual example of the integration of multiple data sets and models from the subsurface and the above surface to give you a feel what I believe can be called a digital environmental twin. A really good example of how to communicate complex subsurface geology with the public is given in this presentation here. It's an online version of a story, a history and background of this road project that has run into difficulties because of unstable ground. We can see historic maps. This is a GIS platform here where you can zoom and pan, and we can see boreholes, we can see groundwater abstraction. We then get explained what the subsurface model of the Dutch subsurface is. You'll hear more about that from Michiel in a moment. We can look at bore profiles, and then importantly we can actually go into 3D and here see full integration of building data in 3D as web services, trees, topography, design of the actual road scheme, and of course now beginning to be visible here the Dutch subsurface model. Not just the lithological variabilities, so here we have the clay and the peat and the sand, but also the visualization of uncertainties. All this in one integrated platform, boreholes, geology, subsurface and surface. Pretty much for me the beginning and illustration of a digital twin that can be used with engineers, designers and the public to make better informed decisions. In order to break down some of these disciplinary and organisational barriers, we have created in the UK the Geospatial Commission, who brings together 6 partner bodies such as the Ordnance Survey and the British Geological Survey, and is trying to address some of those data sharing and interoperability issues. You can read more in our strategy, which we've recently published. You can see our opportunities, and again in this graphic the need for integration across the different disciplines. And we have our missions, and mission 2 is specifically all about improving better access to location data, and I'm now going to go into a little bit more detail about some of the findings we have made in the past 2 years. Whilst working on the UK National Underground Asset Register, which aims to provide a national digital map of all buried pipes and cables, or buried assets, we've established and worked through and overcome many of the very common data sharing challenges. These are to do with liabilities and legal agreements, with commercial risks, with risks to national critical infrastructure, and most importantly, most fundamentally, understanding each other's language, coming up with the data model, the ontologies that mean different organizations can sign up to the same syntax, to the same language, and thereby making their data shareable and interoperable. There is a report there that you can look at and read a bit more in detail. I hope I've shown you that in this ever more interconnected and increasingly complex and changing world, it's of huge importance to share data, information, knowledge and 3D geological models beyond their original purpose with outside organizations and the public, which were previously possibly even unaware of your existence and the existence of your data. So the need for good metadata, the description of what data means, how it was collected, how models were interpreted, what the limitations are, is becoming increasingly necessary. And data needs to be findable, discoverable by humans and machines. It needs to be reusable and affordable. So clear licensing conditions are as essential. All these requirements are summarized in the FAIR principles. I want to close with this slide that captures the core values we hold dear at the UK Cabinet Office, because I believe that despite the importance of the technical, legal and security challenge I've described in the past few minutes, that the real challenge is a cultural, a people challenge. We need to respect the value and data and knowledge from other teams. We need to engage, we need to understand their language. We need to trust other organizations and the public with our data models and the uncertainties. We need to be open with them. We need to build trust and recognize external expertise. And of course, most importantly, we need to build active collaborations and relationships across the traditional boundaries, as I showed in my slide earlier on. Geologists must leave their comfort zone, not treat their science as an end in itself or as something special, and talk to engineers, talk to social sciences, members of the public, and communicate clearly with all parts of society openly that we have essential expertise to tackle the challenges that lie ahead, in particular with a changing climate. So that leaves me to say thanks for listening. I hope that my co-speakers and I today have given you some inspiration and thought about what the future role of geological surveys and 3D geological modelling is, and how we can and must play our part in flattening the other curve that is just right in front of us here. I hope you all stay safe, and I look forward to meeting some of you maybe in person sometime soon, possibly even talking about the role of 3D geology at the UN Climate Change Conference COP26 in Glasgow next year. Thank you and enjoy the rest of the afternoon, evening or morning. Bye.
Thank you, Holger, for that excellent overview of unlocking value from geospatial data. We have good discussion coming in from the chat. So, Holger, there's been a question regarding levels of resolution. Can you please clarify how this activity is being conducted at multiple levels of resolution for different styles of application?
Yeah, thanks for that. I think I've had a couple of answers in the chat already. The resolution question is absolutely valid. We are operating as obviously National Geological Surveys at a national scale and downwards, but we also do cooperate across boundaries towards continental and in some cases the global scale. And at the other end, we have all been involved at very detailed projects such as tunneling and engineering projects. So we operate and build and communicate and deliver models at the required resolution, which is important to the beginnings of a geological survey, where we just mapped at a fixed scale. And as Keith outlined, at the beginning, we just did it because we could. And then 20 years later, we asked, why are we doing it? We now tend to go to the user first, ask what resolution is required, and then fit the model and the interpretation to that scale. So it's truly a multi-resolution approach.
Excellent, Holger. We also have had discussion about whether we are coalescing on standard formats for exchange of models, and to what extent are we married to specific software, or to what extent can this activity be mobile?
Yeah, great question. And again, the book that's coming out soon has a chapter on that. So we're still in state of finding our way with interoperability and data exchange. Most data gets exchanged still in ASCII format or using some of the de facto standards that the GIS and the CAD incumbents have. Some software have one-to-one bilateral agreements, but we are still in the early days, and I saw some comments about oil and gas, and the exploration sectors, of course, have been operating in 3D for a long time, but there was never a requirement to share across boundaries and across disciplines. You were in one package and you had interoperability within. Now we're trying to share between urban planners and city and engineers and CAD designers and geological surveys. We are still in early stages, but we have emerging de facto standards coming out.
Very good. Thank you, Holger. There also are questions about data quality and communicating uncertainty.
Yeah, I'm getting all the easy ones. So absolutely, communicating uncertainty is key, as I just said in my slides. And that does not necessarily only have to be in a technical way. So we have lots of ideas about shading and about running simulations, and Michiel will go into some of that. The live demonstration showed a way the Dutch Geological Survey are communicating uncertainty, which you can hopefully in the chat you can see that for yourself. So there are technical approaches, but I believe important is also that geologists, geoscientists, modelers from all sorts of disciplines also communicate uncertainty in words and in narrative and in pictures and in Minecraft and in all sorts of other ways. So it is definitely a work in progress, but lots is being achieved.
Very good. So thanks again to Holger Kessler of the Geospatial Commission and the British Geological Survey in the UK for that very thought-provoking and informative presentation.